I guess you all know her. She's a local here. She did her PhD in 1999 with dynamical in Galactic, and then moved to Caltech, later to Socorro. And then in 2004, she came back to Germany and then took up a position at the Max Planck Institute for Astronomy here on the Peninsula. And she is a research group leader for extragalactic star formation. And she's known for her work on the Cosmos survey and the PAUSE survey. And today, she's going to talk about the radiation star formation in galactic disks. And so, I'm looking forward to the talk.
Thank you. Thank you very much. For the opportunity to introduce some of the results from the PAUSE survey and put them into some wider context and maybe some outlook. So, the first thing is what happens if you stare at the night sky and you actually stare at it with a space telescope for a very long time. So, I think what you notice is that galaxies come in very different flavors. You have red galaxies, and you have blue galaxies, and blue have more structure, so the red are red and dead, there's your blue disks. There is a lot of star formation online, so it's clearly that not all galaxies, very little are forming stars at the same time. Similarly, if you look in our galaxy and look at the star forming region like the one you see over there, that's the Milky Way.
Are you sure you have it on? Because
as the Milky Way cloud, for example, the Orion, you see in the top half there's a lot of star formation, but then next to the left there's just the red part, there's no star formation, below star formation has already proceeded. So clearly, even if you have gas, star formation doesn't start in one bang. And one interesting thing is you really would like to understand if this small star formation cloud that you can understand in very much detail where star formation proceeds and how it proceeds, how that relates to the star formation activity you see or you don't see in very distant galaxies. And that is actually where nearby galaxies come into play. So here you see in the middle M51. And what you notice with the red points is where the star formation is that star formation isn't all over the disk, but it rather likes to prefer to be concentrated in the spiral arms. So clearly star formation doesn't also not happen in nearby galaxies everywhere. And actually with nearby galaxies we at least have the chance to look at the sizes of an Orion cloud and see how those star formation things will do. Or compared, are they all the same, always the same, or not? You might get the statistics, and from that you could draw conclusions what you see in galaxies at higher redshift. So, regulation of star formation. What regulates star formation? So actually, that very much depends on your point of view, the answer you would be giving. And I'll give you some answers. So, if you're a cosmologist and study the universe, then it's clear it's dark matter. That is what determines the structure, evolution, therefore what is galaxies, that's where star formation is. So that determines star formation. Actually, with galaxies, people start saying, no, inside the galaxies, it's the baryonic matter that determines how much molecular gas is in there. Molecular gas is the fuel, so clearly that determines the star formation, or regulates the star formation. And actually, no, if you look into the molecular gas, it kind of forms about the structures of the giant molecular clouds. And we see a lot of star formation in our galaxies associated with these giant molecular clouds. However, it's in these clouds, if you look carefully, it's the dense gas that's inside where star formation occurs. So clearly, if you talk to galactic colleagues, they'll tell you, well, it's a dense gas fraction, but if you look very closely and high resolution towards in there star formation happens, and if you're down to a dense form, that's actually there you do see a star form. So now the question is from less than an AU up to the whole universe, on which scale is the dominant, is star formation regulated, or are all of these people right in how it's connected? And this is where nearby galaxies come in nicely to help connect the view or the understanding about the explicit detail we have in the Milky Way, what with the cosmology, and maybe to understand how things relate. So today I would like that after presentation you take away these 3 points. The first is very simple. Molecular gas and star formation are closely related. Probably molecular stars form out of molecular gas, so if you you listen closely to Simon Glover and Ralph Pleasant, they might argue otherwise. Then molecular gas properties in galaxies are set by environment. There is not a universal molecular gas property that holds truth across all galaxies without some tweaks. And the last is just to remember that our understanding of the conversion of molecular gas in stars is far from complete, and it seems to be at the moment a very complex process. So, just a quick reminder about the first topic. I assume some of you have been in the summer listening to Anne Levoy's talks. This is a result that came out of the work up at the mountain from the Heracles and Things survey. And what you see here on the right-hand side is plot of the star formation rate surface density against the atomic gas surface density, and you basically see a scatter plot, whereas if you look at the right-hand side, you see that there is a very good correlation, and that's basically all the dots you see there is about 1 kiloparsec size, so you're averaging over potential stochastic effects and so on. It tells you that stars form in molecular gas, at least in those local galaxies sampled, and it's roughly the same efficiency, and this efficiency is referred to as the star formation law or Schmidt-Kennicott relation, and that is what you see here. So, but you also notice there's quite a significant scatter, and the scatter is between the galaxies as well as within galaxies. And the reason for the scatter is actually quite interesting. However, you could think about it that it might be measurements errors, or that it's indeed intrinsic, and that it has physical reasons we have not yet fully understood. So, before moving forward, maybe a quick breakdown, a rough breakdown of the star formation process, and roughly 3 important steps. So the first is you have cold, maybe atomic gas, and out of that you need to form, or in that you need to form molecules and or molecular gas. Once you form molecular gas has to start to become bound, so you start to fill things that are clouds, the giant molecular clouds. Within these clouds, then you have to reach certain densities, that is the dense gas, so you go from 100 or 1,000 particles up to a 10 to the 6th, and then you start to use traces like HCN to basically see them. And out of this dense gas, you have star formation. So this is a rough scheme how to play this process. And the question really is what controls these different steps, which parameters, and there within the galaxies, are they always the same, or do they change depending on the location of the galaxies? So, as Kees already said, there is the Paul survey, and here you see a list of names of all the people involved. And just to introduce to you quickly what the Paul survey is. Paul was initially I think 2010, if I recall. We used both year-round telescopes. The first is the 30-meter telescope, as well as the interferometer at the Plateau de Buhr, together to observe M51 for about 200 hours. And each of 200 hours, we only could cover the sign box you see on the right, so roughly the inner 9 kiloparsecs. The data results in a number of data sets, which are all available, so if you want to play around with that, you can find it there. So why did we pick M51? The first reason is M51 is a roughly M-star, L-star galaxy, so it's a typical star-forming galaxy, has a star formation rate that also makes it, so it's a good representative of what's going on in the star formation in the local universe. When we were slightly cheating, it's also extremely molecule rich. It means observing the molecular gas in it was easy. So the one thing that we pushed very hard on was to get a very good resolution, both in spatial scale as well as in sensitivity, to target something like roughly a typical molecular cloud in our galaxy. So at least to get the upper part of the molecular cloud mass function. So, now coming to the second point, which might not be as familiar, because that's something that has been emerged over the past, let's say, 5 years or so, coming from various surveys. Molecular gas properties in galaxies are set by environment. So, this is coming back to this cartoon. This is now just focusing on what do we understand about how molecular gas comes into clouds. So why was pulse so interesting? So what you see here is just a resolution of a survey of the first result. I showed you this is the typical resolution of that survey. It was about 500 parsecs. And you see nice blue spiral arms, and you see something in the interarm. However, actually, if you want to study clouds, you kind of need to resolve clouds. And I just told you clouds are about 50 parsecs. So you need an increase of a factor of 100 in resolution. And this is then what happens if you increase the resolution. So what you see here, you now start to see that the spiral arms aren't completely smooth. They have wisps sticking out. They are bifurcating. The interarm material isn't completely smooth. So I also described to you now there's a very distinct regions in M51, and actually that's what we use, because you can say, okay, these are different environments. I have the arms, I have the interarms, I have the central region, so you see arms is purple to blue, interarm is green, central region is reddish. So now...
Sorry, you had talked a few times about molecular gas turning into clouds. In the map before, is all the gas we see there molecular gas, or is it all in clouds?
It's all what you see is molecular gas, but not all of it is in clouds. So then we ran an algorithm to decompose the emission we are seeing. So we are here using carbon monoxide as a tracer for molecular gas. If we run an algorithm to break up the emission to identify what are coherent structures in the position-position velocity space, we can associate roughly half of the emission, or depending, in bound structures, and the rest seems to be some more diffuse emission in between. And that is actually true, I think, also for the other galaxies, for a large number of other galaxies, and for some of the other galaxies, depending on some topics. So what you see here, by looking at molecular cloud properties, one could just think about, okay, I'm very simple. I'm looking at the number of clouds above a certain mass limit, so this gives me the mass function, what you see here. And if you look here again, going from the bottom, green being interarm, to the blue-purple arms up to the nuclear bar or the center, you see, you notice first things. First, of course, aren't looking all the same, and they're not all in the same level. So that means if a curve is higher, you have a higher number density of clouds, and the further out the curve reaches, the larger the cloud is you find in a certain area. And that means basically in the arms and the center we have more and larger clouds. And this can kind of be understood that indeed in the spiral arms it collects molecular gas, or the clouds. The clouds can stay longer in the arms, so they might be able to agglomerate or merge or collide. So the exact mechanisms how clouds might grow in the spiral arms is still quite a debate amongst theorists, who are the only ones who actually can observe it over time, how it happens. And then within the interarms, clouds get dispelled, so that's why you have smaller ones and you have less. And with dispel, of course, you have star formation in the spiral arms, as you saw before, and also in the disk you have shear. So one thing that is kind of peculiar is if you look at the red line out there, that is the very center, and those clouds seem to be limited in their growth. And we can think of a number of things. So the center is where the bulge is, so bulge has a higher stellar density.
What's the difference between agglomeration and merging conditions?
You're the theorist, you tell me. I thought the agglomeration is that they are going, it's less violent, or you're having a big thing that starts to grow.
Okay. So more like accretion.
Yes.
Smooth gas.
Something. Yeah. And then, so for the center, you're looking now at, it might be that the radiation field is changing, so changing the physical conditions of molecular gas slightly enough so that you cannot have the, that it's preventing large clouds to grow. There's an AGN in there, so that might have another impact. As well, there's a central bar, so you might have higher shear. So, the one thing that was very intriguing, and unexpected was that indeed the galactic structures of the spiral arms influence the cloud properties, and this was something we definitely did not expect to see. So, taking again the GMC mass functions, there are three things you can see, right? There's a number density, the slope of the function, and the truncation mass. So if you want to compare more galaxies, these are the three things you can easily identify. And so this is some new work NEUS has been working on. So for these 6 galaxies, so on the left-hand side, these are dwarf galaxies. In the middle, there are some more massive galaxies. One is a normal star-forming galaxy, and 31, I guess most of you know, it's more a Green Valley galaxy, and then more two nice star-forming spirals. And all of these 6 galaxies, what they have in common is that they have explicit data that is at the resolution of roughly a typical Milky Way cloud, and it comes from single dish on the left out to Omaha and the former California array for millimeter research, and also the false data. So what happens if you compare the global mass function, just those properties? So the first thing you notice is that if you look at the numbers, surface density of the GMC mass functions, you see that it is lower in the dwarf galaxies that also have a lower stellar surface density, and that it rises with stellar surface density. And you see a similar trend of the fraction, how molecular the gas is in the area there the molecular clouds were observed. And if you go to the slope of the mass function, you see that the slope becomes much more shallow the higher the stellar surface density and the higher the molecular fraction of the gas, of the cold gases. And going lastly, just looking at the truncation mass, you get larger GMCs, if you have a higher stellar surface density, and of course if the molecular fraction is higher. So it clearly seems that the stellar surface density seems to have some correlation with what kind of GMC distribution or population you expect. So if you go into the theory and you believe that, then you would expect that the stellar surface density kind of sets how much molecular gas you have, and then it means it must be the stellar surface density that determines at least the properties of your clouds or the distribution you're seeing. So some might wonder how that could be. Depending if you talk to some senior people, they think a cloud is completely decoupled from its environment. So it shouldn't have nothing to do. And this was something, this is an updated plot from the USE 2013 paper. What you see here is the total pressure in the midplane on the x-axis. So that means the hydrostatic pressure you expect to see from calculating from the gas plus the stars versus the internal GMC pressure measured from their kinematics information. And what you see, it's roughly that the clouds are in roughly pressure equilibrium. So that means the clouds know about their environment, and maybe adjustments to the outer environment or should have an impact. And I'll come back to that point if I talk about streaming motions. So maybe let's move on. Molecular gas clouds. What about the dense gas fraction? That is something everybody would be very interested in. Unfortunately, I only have a quick sneak preview. That's work led by Frank Deville, who probably is very familiar to quite a few of you here. And what you see here is the ratio of the emission from dense gas in dense molecular gas over the normal molecular gas versus the stellar surface density. And if you now only focus on the red points, which are the bint version of all the gray and black points, you could also see a trend. And that is quite interesting because to see and what's happening. So this is part of its first study of the Empire survey. Frank is leading. It's a large project at the 30 meter. They are mapping 9 galaxy disks. And the aim is to really confirm that the dense gas fraction is set by density, so here, like the volume density, and not that there is a certain threshold above which gas becomes dense, or gas becomes then star formation. So this is about to understand better what triggers the star formation the star formation in a cloud, and there are competing models. I will not go into those. So now, coming to the last point I want to do, and this is where I will spend most of my time, it's about the conversion of molecular gas into stars. And it's a complex process. So here I'm going to cheat. I will not look at the intermediate step about what is the dense gas doing, but rather what is, how is molecular clouds, how do we go from molecular gas to star formation right away. So I would like to come back to the GMC mass functions that you see here. They are split up all by environment. And similarly to the mass functions on GMCs, you could also measure those of young stellar clusters using HST imaging. You kind of get the age as well as the mass out of the luminosity fitting just fitting to their broadband colors. And so we use a catalog that was available. And if we look at the truncation mass, for example, amongst many possibilities, these were tracked in each environment. So if the GMC mass function had the highest mass in a certain environment, also the young stellar cluster mass function had the highest cluster there. Interestingly, though, if you look at the slopes, it turned out that in the interim, the slope you're measuring was exactly the same between the young clusters and the GMCs. There was an offset of about 0.3 gas in the arm, which is exactly what you expect if there is radiation pressure, and there was a theoretical paper saying this is the offset you expect because of feedback processes. This is what you see, and then the orange line was totally off. There was an offset of even 1 depth, and we don't know why. So there's the feedback. So that's something else that would be interesting for you to remember. So going back to the data. So the first thing to realize is if you look at this molecular gas, and if you were a strong believer in the Koenig-Schmidt relation, you would tell me star formation is high everywhere there. You see at least the cyan green emission going. So actually you can check that very easily by using a tracer like the mid-infrared emission that comes from hot dust, from dust heated by star formation. And the things you notice, yes, in the center part there is a nice correlation, so white contours are the CO emission. And then if I look at the spiral arms, the star formation seems to be slightly offset. And then there might be regions where I do see quite some molecular gas, but no star formation. If you stare long enough at the images, you see all that. But to make it easier for you, we now binned up all the images you saw before into sizes of areas of 800 parsecs, and compare just the ratio of the infrared luminosity as a proxy for star formation over the CO luminosity, which is basically the star formation efficiency. And what you see in the center, the star formation efficiency is very high, and it's much lower around it, and then it starts to become high again in the arms. So you have about a factor of 3 or so difference already just across the small area we probed. So now you're of course very interested to understand what is causing the variations of this relation in M51. And the thing what Adam Leroy did here, in each of the circles you saw before, he was looking at average properties at the resolution of the clouds. And the properties he was looking at was the surface density of the gas, the velocity dispersion, which might be a proxy for the Mach number, as well as the boundedness, so how much of the gas might be bound together or mineralized. And so you see these 3 properties plotted here against the star formation efficiency as being interested if there is any correlation. So the first thing you notice, there is no correlation if you look at the surface density. He's even splitting up the things between inner disk, which is everything that I call inner region, and then molecular disk is what I would call arms and interarm region. And no matter which region you separate, there is no trend. So Normally, if you look at velocity dispersion, there is also no trend between the two quantities. However, if you come to the boundedness, this is the first time you start to see a trend here. You see here, and so this probably tells you that star formation depends on the property of the gas to become gravitationally unstable or more bound together.
If I can say one more time, each circle there represents an area of 40 parsecs or 800 parsecs?
It's the average of an area of 800 parsecs. So this is interesting. There's some other evidence that also tells us maybe the contrast between inner pressure or between the cloud and the outer has something to do that, and that is work by Sharon Knight. It's basically what's the impact of dynamical pressure on the gas stuff. So recall I told you that molecular clouds are close to pressure equilibrium. So that means changing something a little bit might have a significant impact. So if you remember the dynamic lectures, maybe, gas in motion means if you have streaming motions. If you have spiral arms, usually it's a change to the gravitational potential. Therefore, you expect there should be streaming motions, and I show you see them quite nicely in M51. So, but if you have gas in motion, and if you think of the Bernoulli principle, it means that you're starting to reduce the pressure. So, if you have the pressure reduced, it means the clouds can come stable, have a higher mass and stay stable and not start to collapse. So if you now change the number of clouds that can form stars, you have less star formation for the same amount of molecular gas you see. And if you have that, then of course you observe a lower star formation efficiency. So one prediction of this model is that you should see a trend between the streaming motions you measure in the gas and how much star formation efficiency you have. And if you look at that along a spiral arm in M51, now you see the amount of streaming that is present is represented by the size of the symbol, and you look at the star formation rate, surface density versus the molecular gas surface density. This is the plot I showed you first. The star formation efficiency goes up, so low star formation efficiency is at the bottom, high is at the top. You basically see what this model predicted. So it's very clear clouds are very sensitive to the emission they're having. So, changing topic a little bit. So we know now star formation happens in spiral arms. There has been a very simple picture. If you think about it, this is my Pullman's representation of a spiral arm, and the spiral arm density rotates rigidly. As I told you before, there's evidence that it gathers molecular clouds. They might collide. You might have formation of dense gas, like in the location where the gas is gathering, and star formation should ignite if you think everything happens almost instantaneously. And then if you observe this arm after a certain amount of time, let's say a few million to 10 million years, you should see a nice separation of the former location of the arm, where now you find star forming or stellar clusters, and the arm, the molecular gas rate should be. So this is a simple picture that people like to see. So now with M51 they actually have all the data because people like to observe this galaxy to actually test this. So I'm picking just the modern part for some reason I just liked it better. So if we look at this spiral arm, you now see basically, you see the arm in blue, and then you see these things sticking out that are called spurs or feathers, and the locations I'm marking are ones that are defined on dust images from the HST by Lalline et al. And if you wonder about the nomenclature, There's a very nice paper by Deborah. This is the classical one, how people decided to call these features. So now we know we have gas in the arm and gas in the spurs, so there's star formation. And in order to find that out, we tried all different tracers you can get. So on the first, in the top, you see basically free emission in the radio. So this comes from H2 regions. It should have no impact at all from dust extinction. So it should be a very good view of very young star formation, where you have all these stars forming. In the next panel, it's hot dust at 24 micron. Similarly, hot dust should be heated by young stars, also very young. And you see in all the full circles, that's basically where you have most of the star formation occurring. In principle, 24 micron and free emission should trace the same. If you look very closely, you'll notice that around the middle circle below, there's emission at 33 gigahertz, but not at 24 micron. So that might tell you that there might be some age difference, I don't know. So if you then go below, you look at H2 regions, and the stretch I'm using here is basically to show you the H2 regions in all the shells. So you're looking at fairly evolved H2 regions with more than a few million years age. And again, most of the H-alpha emission you're seeing is off the spiral arm and associated with the spurs. And last but not least, it's the distribution of young stellar clusters. The color coding is just similar to what I call the arm and the spurs. And again, the young clusters prefer to lie on the spurs, or their former spurs have been. So if you put that together, this is roughly an age trend where star formation is happening. You see, the star formation is always happening in the spurs, and not, as I told you, in the arms. And so I don't know. I don't know what it means. I can also tell you that there is the variation of the star formation age among the different spurs is also varying, so it's not all uniformly at the same age. But that raises an interesting question. So the feedback, I told you before, the feedback should act on the amounts of molecular gases. A significant amount of molecular gas is sitting in the spiral arms, but that's not where star formation appears to happen, or where you see stellar winds or radiation impacting the gas, so that might give some problems to just including stellar feedback here. One other thing that is quite curious about this here is that the dense molecular gas, if you see, as I told you, you should have the molecular gas. Due to the gathering, we kind of expect that the gas is going to become more dense, and that is supposed to happen in the spiral arms. So if you look at compare the top panel with the second panel, that is where we have HCN emission. It was a quite heroic effort using plateau de Boer, and 50 hours of observing time is what we could get out of it. So there you see that a significant, the emission tends to be more in the spurs, would also go against our naive picture of what's going on. Interesting is also, if you look at the atomic gas, you could think about atomic gas and molecular gas are both very well mixed. So we would expect both to see them light. And so the second panel from the bottom, you see that the H1 emission is roughly between the spurs, or but clearly offset from the spiral arm. And the best explanation we can find for it is that the enhanced atomic gas we're seeing here is actually a dissociation product. So the H1 we're observing associated with the spiral arms isn't atomic gas that is gathered there, but rather it's just a dissociation product from the molecular gas after the star formation has happened. And below, just again, I show again the H-alpha emission. So, if we come to this, basically I think my idea is that at least the simple picture is wrong. clear that it's too simplistic. We must miss some of the physics that are there. One might be formation times or lifetimes. How long does it take for gas to collapse or go from a collapse then to star formation? And the other might be stabilization. So at least on one of the topics, on the formation time, we can try to get some estimate. What is the typical lifetime of a giant molecular cloud, even outside molecular gas? And this is work Sharon published last year. So what you see here now is taking your disk, your spirals, and unwrap it. So what you see, if you go from bottom to top, is a radial distribution, and then from left to right is the azimuthal phase. So you're looking at a polar representation of the segment between two spiral arcs. So the blue are molecular gas, the yellow stars are star formation, and the thing in between is the interon region. And you could start to think that, okay, I can count how many star formations, and basically how long it takes you from your clouds to travel from one arm to the other arm, or just across the interon. So it might give you an idea how much lifetimes you have. So the thing that you can do, you can try to count how many clouds you have. And you compare the number of clouds in one part of the interon with the second part. And if you do that, you can roughly get out what's the typical travel time. And out of the travel time, you can get an estimate of the lifetime in molecular gas. So if you do that, if you basically go up from bottom to top, so in radial bins, you count up how many clouds do I have in zone 1 versus zone 2, and I know how long it roughly takes for the clouds to go across the interon. You can get an estimate of what is the typical lifetime, and that is basically what you see here. So you do the lifetime as a function of radius along the spiral, the interon region in M51. So the first thing what you notice here, this is so big, there is not that much star formation, and the line in the data is the solid line, and that is the travel time you estimate, and compared to that is the shear time, which is the dotted line. And then you see some deviation in the regime there, there is star formation, so this might have affected that our statistics aren't so good. So if you read off the numbers, you get GMC lifetimes of about 20 to 30 mega years. They seem to be set by the shear time scale, you see. And this value is very similar, but using different methods, what has been found in the LNC, M33, and Milky Way. So, staying here, so I think I made my 3 points. To remind you again, molecular gas and star formation are closely related. Molecular gas properties are not universal in each galaxies, but the environment matters in which galaxy they are, as well as where in the galaxies they are. And understanding the conversion of molecular gas into stars is a complex process, and we have just started. So, what are the next steps? I think we definitely want to understand the role of the dense gas, because it seems to be quite critical in the galactic. We want to better understand feedback and quantify it. We want to understand which parameters really drive the evolution of molecular gas. And how do we go from there? So now stealing some plot more from my colleagues working in galaxy evolution. This is a very famous plot. If you plot the star formation rate against the stellar mass of a number of galaxies, so here these are about 50,000 local galaxies from the Sloan survey, together with Galactic as a measure of their star formation rate. You see that roughly they have a blue line is what you call the main sequence of star-forming galaxies. So this is what a typical star-forming galaxy looks like, and there you have the very dark area. This is where, roughly in the local universe, you could say, about the majority of stars are born in these types of galaxies. So I told you that M51 is a very good representative of a typical L-star main sequence galaxy. So what about the other galaxies people have started like to stay in the local group, and they love the LMC and the SMC as well as M33. But these are dwarf galaxies, so we're moving off to one end. People also like to look at M31, but M31 is actually a Green Valley galaxy. So if you really want to sample a large area, I think you need to basically to fully sample the phase space. In order to do that, probably you need 30 plus galaxies to go, and you have to go to beyond the local group. So luckily there is ALMA now, but observations of a galaxy with ALMA to get a data set similar to M51 will take about 5 to 10 hours, and now you can do the math, how long this will take. So clearly there might be 30 plus galaxies at some point. The question is if the data set is complete. And if you really want to understand which parameters are driving the star formation efficiency of a process and which are important beyond stellar mass surface density, that will be a significant effort. So I'm pretty much convinced that ALMA must do a survey of molecular gas at cloud scales in a significant sample of nearby galaxies. And only then we can uncover and really quantify which of the parameters are the main parameters driving the star formation, as well as what are the secondary, and if it's always the same set and priority or not. And if we do that, I think we can start to think about establishing a theory for star formation. Thank you.
Thank you very much, Elena. It was a very nice talk and for a very interesting case for ALMA. So let me make a little bit more light. And now let's open for questions. As usual, we first have the students and postdocs. Questions from students or postdocs? No? Yes? Okay.
I had a question about the boundedness idea. This is actually sharing the idea. We talked about this last night. The assumption there is that the line of sight velocity dispersion you see is due to random turbulent motions, and then you can call it boundedness. Refer to the theory of error. But instead of in these fairly large apertures, the observed dispersion is due to variations in streaming motion, then it's not boundedness. So what you see in that trend could also be exactly what Sharon showed in her 2013 paper. That correlation in star formation efficiency correlates with streaming motions. So yes, that's on the right hand side there. Now I should probably ask Leora this question, not you, but I was wondering what your thoughts are.
So first, this is measured at 40 parsecs, and Adam is taking into account some of the streaming motions to correct for that. So it's not the dispersion, it's not plot, the left-hand plot divided by the right-hand plot. By the middle plot you give you left-hand, but it's the individual properties measured. So in that sense it's different. I also wouldn't say that this is Adam's idea, this is Adam's way of plotting data to test ideas. And this is very much work in progress. I don't think that, I think streaming measurements play some role, but I don't think what you're seeing here has something to do with galactic rotation, which we were kind of implying might be the case. So that was definitely taken out. Of course, then disentangling intrinsic cloud properties versus from others will be harder. How that is exactly done. I mean, I think you will never be able to do that perfectly at this resolution.
Okay, let's open for everybody. I'm always wondering how representative the example that you picked is. You showed these
relatively small region at the top part of this plot where you looked at great details at the different traces. But looking more closely to other parts of the regions, it is much less clear what the time sequence might be, isn't it? Or so what are the variations in these
I also looked at
tracer sequences, let's say?
So my issue with the trace was, so first is I also look very closely at the opposite thing down here, and it's even more a mess. So that's why I thought the other one is slightly easier. It seemed also kinematically better behaved. About the timing sequence, I think the star clusters are all between 3 and most of them are more closer to 10 megayears old. The thing you clearly see is this thing here. You see that there is an H-alpha shell that is dissolved. So probably there the star formation had already happened, has destroyed molecular gas that is there. The difference between, I think, 3 hot dust should timing-wise roughly be the same. H-alpha, I think there's everything from 1 million years to then you have your large H2 regions, which is, I don't know, 5 million years. So this is tracing a very large range, and this is tracing another large range. And if you try to find out, okay, I do have very bright, I try to do that game, I have very bright 24 micron, I have faint H-alpha, and so on. You would say some of the regions, yes, this is younger, this is very old, this goes from older to very young with all the traces. So it's not a clear sequence, which might also be have to do with the stochasticity of the star formation process happening in spiral arms. But the thing is, this is nothing, for example, Claire could reproduce with her models so far, which have cloud resolution, and also I think the high resolution models from Ian Bonnell, they still expect that the collapse starts in here, and if they turn on star formation right away, the general picture, it wouldn't produce necessarily that offset. And yeah, I showed it to Eve Oysterbeck, and she was happy. Yes, that's exactly what I expect if I turn on magnetic fields. Clouds will be stabilized, and only if they get start sheared out in the spurs. This is that. It's perfect for my model.
So yes, I did want to refer to Eve because she's essentially running a model of gravitational instability. And I'm going to say this at much more length in my talk next week at the Hill. But it seems to me that many of these observations can be understood in the context of spiral arms are the first indication of gravitational instability in differentially rotating disks. And star formation is a consequence of gravitational instability, and molecular gas and dense gas formation are things that happen as you collapse towards stars. So the example I would take then would be a galaxy that's not so differentially rotating like the SMC, where you still have plenty of star formation without agglomeration in arms. Do we need to invoke arms sweeping stuff up, or can we just invoke collapse and, instead of boundedness, talk about objects that are simply collapsing more or less quickly?
Oh, I think the picture Adam wants to advocate is that it's the whole cloud model. I think it's the paper, it goes more into each direction. It's the contrast between how dense is the cloud compared to its surroundings. And if the contrast is higher, the things start to collapse more. So what is causing then that contrast? And go back to the questions you posed. So this is against the threshold model that is advocated by others. And remember from the arms, I can say there is kinematic evidence that gas is streaming towards the arms, so clearly that would argue for being gravitational very stable. How much that effect works together with some of the others, it probably goes back to understanding turbulence, and let's leave it to your neighbor.
I want to ask about the linkage of the plot we have up here to your take-home message number 1, right? So it used to be cold gas is linked to star formation, and 5 to 10 years ago that was revised to, oh no, it's molecular gas is linked to star formation. If I look at that plot, doesn't that need revising again? Oh no, it's not molecular gas, it's the very densest part thereof as traced by CN that's linked to star formation. The rest of the molecular gas may not be relevant.
I think with some of the work Frank Vigilio is leading, they might argue that dense gas fraction is not necessarily linked to star formation either.
Well, but you see in...
that we are not understanding. I think that's what people would like to do, the linkage.
But really, empirically in this circumstance, you see CN map predicts the locations of star formation. The CO map much more poorly. Isn't that what that's at least what I thought I gathered from, you don't quite have it, but if you were to overlay 24 and HCN, right, that looks pretty good.
Well, exactly, there's some HCN issue, but the problem then also comes to, and I think that's something we need to understand better, what is exciting HCN, and is it just a clean tracer as we think? So that is one thing as well, and the thing is also there's a recent paper last year came out by Schinnerer et al. Where they looked at the HCM or the dense gas fraction in about 30 different regions across nearby disk galaxies, and there they already see an indication that the dense gas fraction might not have an S-tight. Well, the dense gas might not have an S-tight relation to star formation rate as you get if you plot everything from local star formation cores up to total ULO's top. But there are trends in between, and that is the very Empire project aims to make a big dent in our understanding.
Do you have some information about shock waves running through your star-forming regions? For example, a correlation between supernovae and your regions, or density waves, or magnetic galactic field.
So there are, as far as I recall, the observations of the magnetic field in M51, it's fairly regular with the spiral arms. They're low the resolution. The spiral arms have a bit of about 5 to 10 arc seconds, and that's roughly the resolution in the radio continuum. They can determine the magnetic field. So there is no higher resolution map published, to my knowledge. So much for magnetic waves. We have the kinematic information from the molecular gas, and the thing we see very clearly is that the spiral arms are changing the motions. It's very consistent with streaming motions to change. There are deviations at higher resolution. The problem is then our sensitivity isn't good enough to be sure how much each individual wiggles we could trust. And I'm not aware of a high resolution H-alpha map, which might be more for the outflow. And I don't think for X-rays people have looked in exact locations. I know people look at X-ray binaries, but not. And supernova remnants, yes, there are quite a few supernova remnants in M51, but I don't recall the exact locations.
So you know I'm working with M31 and all these high-resolution M31 things, and I was wondering about the TIR over CO ratio that is proxy for star formation efficiency. And in that particular galaxy, I think the star formation is high, so you can use it all the time in those regions. But do you think that those spurs and all those deviations from the model you're trying to show are just based on low star formation efficiencies or non-good proxy using 0 over CO?
The reason to address that was indeed to go after radio free continuum, and I think only thing it shows that 24 micron is a very good proxy for star formation on small scale.
But we know also that the phase, well, the gas phase is also a problem when you do that because you can mix. So for this proxy, we know the proxy is bad when you have a mix of phase phases.
I think you need to separate things. The way Adam would like to approach or what the Hamiltons was to look what is the average. So you look at a large enough area that you don't have to worry about spatial variations because things are evolving over time, also spatially. When I was looking at the spiral arm, I was exactly trying to use that there is spatial offsets that should be consistent with models. And I think to answer to really understand that, one would like to have fine-thread data at the resolution of a few arcseconds. There you then could see there's the cold dust emission, there's the hot coming from, but then you have the temporal variations that go into spatial variations. It always depends on the question you're asking.
I have a different question to your lifetime determination in your last slides. In order to determine the lifetime of molecular clouds, you need the relative velocity between the stars and the gas motion and the spiral arm pattern speed. So how do you determine that? We have information about the rotation radius and where the spiral, what's the difference in the pattern speed?
Yes, but for this actually you don't, because you're only looking at the interarm. In the interarm you should just use the angular velocity, and the angular velocity you could get either from the gas velocity field or you also have a gravitational, stellar gravitational potential.
But eventually you have the rotation radius, yeah? Then the patterns move with the same speed.
Yeah, but we're only using the spiral arms to define the area of what to use. You can talk about it later.
Yes, Charlotte. I have two questions actually, both about the tracers and so if you go back to this slide, what would be against B looking at the bottom figure and just saying that your tracer of the star formation is not a zero-age tracer? So it has taken some time before you see this tracer. And so that's why they're not in the same place. That's my first question.
Okay, if you were to see that, then you would expect to see, if it's perfect, that H alpha is sitting here, dense gas is sitting here, and that's what happens. So you would like to see a separation. If it was just that simple, spiral arm is a rigid pattern and rotates. If that simple picture would hold. And I immediately can tell you then you'll never be able to explain that one region.
Well, there's still stochastic things, but just
Yes.
the fact that it takes some time before you can see the tracer.
I also was measuring the radial offset and comparing that to the expectations from the pattern speed, and there's no trend. I don't show that.
And the other question I had was about the boundary transaction. I was wondering, all your tracers are high mass star forming tracers. Is there a regime in which you think that when the boundedness is so low that you're actually making less high mass stars? You still have star formation, but you simply don't trace it with the tracers you're using.
So you're arguing for a very long time there?
Well, I mean, that was the question was triggered by the fact that you were talking about boundedness.
Okay. I wouldn't think so because, I mean, all the clouds in M51, and if you look at them, they are about an order of magnitude larger than the curve you would see in the Milky Way. So there's no need to worry about romance stuff. And I think if you look at the stellar clusters, I think people fitting those, I haven't seen any evidence that they would think that they would need a different argument to explain their master-like ratios. So, yes. Yeah, I'm sorry, yes, I'm always ignoring all that stuff.
Any further questions? No further questions? The next thing, again.